All right. So I got this this mass. I can tell that it's a mass because it says so. And I don't know. Go figure, right? Up until the past, few years, people kind of just put it out there that gravity could get shone out from a mass, and people threw out words like gravitons and things like that. But actually, that's not such a terrible model. I want to put out that gravity could kind of shine out like light from a flashlight, if you like. Now, I recognize that gravity goes out as a sphere, but I want to just think about like a patch of the sphere. Okay, so forgive me. I'm going to use a ruler. If you have a ruler, this is great. And I'm going to do a patch of gravity that gets shone out from this mass. And the way that I'm going to do it is a 3 centimeter by 3 centimeter square. And the bottom corner of that square is going to be at the dot that's at the end of this line segment. Okay, so I'm being really intentional about what I'm doing because I want to show an idea. 3 by 3. And I had to get the scaling right for print for this piece of paper, so it really does work out. Now, the other thing that I could do is, you remember back in art class, and we're being sort of multimodal about this. In art class when we were kids, you remember the first time you drew a 3-dimensional shape and you talked about vanishing points? Of course, Cavendish would have been well aware of this, the brilliant person that he was, but there are other people that have thought this out. Vanishing points, this is a great way to show perspective. And people say, oh yeah, I remember that. I was like grade 7 or something. I was only young then, and now I'm so much more wise and worldly. And what we did next was we drew another square. And so I'm going to do my other square in red. And the way that I've scaled this, it should end up being 2 centimeters by 2 centimeters, if you do it all correctly. So I've scaled it fairly intentionally on my page. Okay, got another square. And if we were in elementary school, we would say, oh my gosh, this is great, I've got myself a cube, I'm so excited. And if you learned about 2-point perspective and 3-point perspective, that's a whole other thing where we could add on to this. I think on your worksheet here, there's a little image about how 3-point perspective works, or 2-point perspective, and you could play around with it, okay? So I love this in art, but in physics, I want to draw another one. I'm going to use green. Turns out that this one will end up being 1 centimeter by 1 centimeter. By the way, the dots that are along that line segment that we're making use of right now, those dots are all equidistant from each other. Basically, I broke that line segment up into thirds. They're all equidistant from each other. And what that means is that if I was talking about how far each of those squares is from the origin, or from the center of mass, I could say that I've got R1. Actually, you know what? Maybe I don't even want to call it R1. Maybe I just want to call it, instead of R1, maybe I'll call it 1R. So if I call it 1R, then that means that the next one would be how many R's away? 2 R's, yeah. RR. Yeah, some pirates. 3 R's. RRR. Okay, so 3 times further away. Something neat happens here. And one time I saw this online. It was a little cartoon that talked about how this reminded the author, the original poster, of a peanut butter gun. And I thought, a peanut butter gun? That's a weird thing to say. And they went on to say, oh yeah, well, if you had a peanut butter gun that shot peanut butter out onto toast, you could cover toast a lot quicker than spreading it with a knife. And then everybody who has a peanut allergy is like, oh my gosh, that sounds like a death ray. But then as I look at this, I realize it's not such a bad thing to talk about, because if each one of these squares, the green one, the red one, and the blue one, were increasing slices of toast, can you see that this peanut butter gun would produce very thick toast, very thick peanut butter on the first slice, and very thin peanut butter on the last slice? And I could even say, how many units of area are there here? 9. How many units of area here? 4. And 1. And it turns out that if I think about this idea of the peanut butter gun, I could say that 1/9 intensity, 1/9 of the intensity occurs at 3 times the distance . 1/9 of the intensity occurs at 3 times the distance. And for peanut butter guns, that would mean that the peanut butter would be 1/9 as thick here as here. When it comes to gravity, that means that when I'm 3 times further away, the gravitational field intensity is 1/9 of what it is here. You see what I'm talking about? I like this kinesthetic thing of the peanut butter gun. I thought it was cute. But really we're talking about gravity, you know? I feel like this is something that we can kind of hang our hats on. Remember, we're not letting go of anything that Cavendish said. You know, G still equals 6.67 times 10 to the power of -11 Newton meters squared per kilogram squared. And F big G still equals G m1 m2 over r squared. But what we're saying is that r squared that Cavendish got at by graphical methods could also be gotten at by geometric methods. You see what I'm talking about? So we're just backing up Cavendish and saying, yeah, this really does make sense, peanut butter guns. And while he got at it, finding the slope of a linearized force due to gravity versus m1, m2 over r squared graph, we just kind of supported that by talking about geometric spread. Okay? And then there's people that say, well, wait a minute, aren't we really talking about gravity going out as a sphere, not really as a pyramid? And you can say, well, okay, sure. If this is the planet and gravity kind of spreads out in all directions, couldn't I define for myself a square on the surface of a larger sphere, like a bubble, that projects from that center? See how that's like a surface, a patch on a sphere of gravity spreading outward spherically? If I take my page and I rotate it, and I say, okay, so that patch on the bubble could be thought of very much like that pyramid that we just drew. Can you see how the patch on the bubble really is the same as the pyramid that we just drew? And we can split it up however we like.
It all makes sense now.
Where this would be 1r and this would be 2r. Same idea. And then there are other people that say, well, I'm not convinced. Aren't we talking about gravity spreading out over spheres? Tell me about the surface area of a sphere, because we're not talking about just a patch, we're talking about the whole darn sphere. Surface area of a sphere is 4 pi r squared, just in case you didn't know. And so what we're talking about is an intensity that's being spread out over a surface area, which means we're talking about an intensity that's being spread out over the surface area of a sphere, which means that there's still going to be an r squared in that denominator, however we think about it. And so now we've kind of come at this from 3 different angles, talking about how this has got to be what people typically call an inverse square law.
Inverse square law.
Okay? This idea of an inverse square law is something that drops off as r increases 1 over r squared. Now, if you wanted to play around with this and try out inverse square laws with, like a quick experiment, take your hand, put it in front of your face. So here's a person, and we put the hand way out here. Here is the hand. And then we take another hand, and we put that other hand in front of your face, but not as far away. Okay, this is my expert artwork, okay? The first hand is a distance r away. the second hand is a distance 2r away. In other words, twice as far away. Go ahead and try it. What I bet you can do, I bet you can very easily take that near hand and more or less make it fit 4 times by shifting your hand around in front of the other hand. You want something that's a little bit easier to deal with? Take a piece of paper and put it a distance r from your eyes. Put another piece of paper a distance r from your eyes. What you're going to see from your perspective is the piece of paper further from you will look like a small piece, and the piece of paper closer to you will look like a big piece, and you should be able to shift the near paper around to 4 different positions and cover the same area as the close paper. Check to see if you can do it. Here I am trying to describe a 3-dimensional experiment, but you have the equipment in your hands literally. Okay?